I wish someone would teach me the difference between Gaussian and log-normal distribution.
In order to understand the difference between the log-normal and the Gaussian distribution, it's first helpful to understand what a distribution means in general. In order to do that, we're going to shoot LeBron James with Nerf darts. As you can see, some of the darts struck right near LeBron James, some struck distance away, and some struck early. As we see from that little experiment, due to some of the inaccuracies in our Nerf equipment, some of the darts landed very close to LeBron James, some landed far, and some landed short. If we were to count up the number of darts that landed at each distance, we'd be able to build a histogram for a distribution. So let's say that 4 darts landed within about 6 inches of LeBron James. So we'll put 4 right there. And then 2 darts landed between 6 to 12 inches short, and 2 more darts landed 6 to 12 inches long. And then we had 1 dart that landed beyond 12 inches short and 1 dart that landed beyond 12 inches long. We can then plot the count of darts that landed at the different distances. And because the error in the Nerf gun is essentially random, it's not bounded on either side, we wind up with a Gaussian distribution.
A normal distribution, sometimes called the bell curve, is a distribution that occurs naturally in many situations. For example, the bell curve is seen in tests like the SAT and GRE. The bulk of students will score an average of C, while a smaller number of students will score a B or D, and even smaller percentage of students score an F or an A. This creates a distribution that resembles a bell, hence the nickname. The bell curve is symmetrical. Half of the data will fall to the left of the mean, half will fall to the right. Many groups follow this type of pattern. That's why it is widely used in business, statistics, and the government bodies like the FDA.
We can use the LeBron James and Nerf darts experiment to illustrate the log-normal distribution also. Remember, a log-normal distribution applies when there's a boundary in the data. In order to test this, we've placed LeBron James up against a wall and will now shoot with Nerf darts. As you can see from this illustration, because we have the wall, we have no darts missing long, but we still have darts missing short, and darts landing close to LeBron James or being deflected back close to LeBron James. So again, considering our same sample of 10 darts, but this time with the wall, we notice that the vast majority of the darts were fairly close to LeBron James. We'll say 5. There may have been room for 1 or 2 of them behind him in that brief space before the wall. We'll put a 1 there. There were probably maybe 3 or 4 about 6 to 12 inches away from him. And then there may have been 1 which was so poorly aimed that it was over 12 inches in front of him. And this data set is indicative of the log-normal distribution.
The log-normal distribution is good for representing data that can only vary in one direction, as opposed to varying in both directions like the Gaussian distribution. You see this sort of effect when you measure data that has a boundary, such as 0, if measurements cannot be negative. This type of distribution is appropriate for occupational health data that is close to the limit of detection or close to 0, and it puts additional weight on very high values, creating a safer estimate of the 95th percentile.
So the value that these statistical tools provide to the scientist or industrial hygienist is that because error is reasonably predictable, as you shoot more and more darts, you can develop a pattern or a prediction of what will happen in the future. If you know the type of error that you're dealing with, bounded or unbounded, you can determine appropriate statistics that go with that. The distributions mathematically have certain parameters that go along with them, such as the 95th percentile or the standard deviation. And these allow us to predict, based on past data, what will most likely happen in the future.
So what does it all mean? Just pay attention to the board and find out.
Oh, now I get it.